I'm going to start this video out by just giving you the opportunity to try to find the area of the region shaded in this figure. And I want you to know that this one's going to be a little bit tricky. So really think about it, really take a look at this graph and see what you can see. All right, go ahead. All right, welcome back. First of all, let me just label each of these functions. That's f of x, the linear function is g of x, and the quadratic is h of x. What I'm seeing in this graph is two distinct things going on here. I can see that at this point where those two graphs intersect each other, I've got a couple of different things going on. Pretend that's a vertical line. I notice here on the left-hand side that I've got the function f of x as the top function and g of x as the bottom function. However, if I look at the right side, let's see. If I look at this right-hand side, that's not a very good color to highlight in, but I can see that I've got two different function arrangements. I've got f of x as the top function and h of x as the bottom function. So I'm going to write this using two different integrals. And something I didn't mention in the last video, but some of you are probably doing this anyway. There's a couple different ways you can write this. So from 0 to 1, I can write this a couple different ways. From 0 to 1, I notice that f of x is the top function minus the bottom function, which in this case is g of x. And some of you might have been doing this in the last video, and if so, I'm going to verify that what you were doing is correct. You can write this as one single integral of f of x minus g of x. Because of the properties of integrals, you can combine those two together. And if you write this in symbolic form, f of x is 9, and g of x is negative 8x plus 9. So if you simplify that, it's going to make this problem a lot easier to solve. 9 minus negative x, so that's positive 8x, and then 9 minus 9 is just 0. So now finding the antiderivative of 8x and plugging in 9 and 0 makes your work a little bit easier. All right, plus we have the area on the right-hand side where we've got two different functions working together. And this one's from 1 to 3. In this case, I've got f of x as the top function and h of x as the bottom function. And again, I can write that as one single integral if you prefer. I keep saying g, but it's still h. And if we write that symbolically, it's just 9 minus x squared. So now if you do the math and you find the antiderivative, use the first fundamental theorem of calculus, or the first part of the fundamental theorem of calculus, you can actually calculate the area under or between all three of those curves, because I can see there's two different sections going on. Okay, this last one is dealing with equations that are written in a different form. These are both written as x equals 2y plus 4 and then x equals y squared plus 1. So we're looking in a slightly different direction. The equation on the left is pretty easy to solve and get y by itself. The equation on the right, though, would be a little bit tricky because when you took the square root to isolate y, you would have plus or minus the square root. So there's all kinds of ways you can make mistakes there, and it just takes longer. So let's think about it this way. What you're used to is an equation being written in the form of y equals mx plus b being the y-intercept. Well, in our case, since this is x equals, this is now the x-intercept. And normally we think of the slope as rise over run. So now, since we're looking at things with respect to x, this is run over rise. So let's graph this first one. I need to fix that. I'm not okay with that. Let's try this again. And thank you, Notability, for the straight lines. All right, let's graph this linear function. We have an x-intercept of 4. 1, 2, 3, 4. We have a run of 2 and a rise of 1. So now I can draw my linear function. Okay, similarly on this one, Normally on a parabola, this plus y is the y-intercept, but since this is x equals, this is the x-intercept. Normally the parabola, since it's a positive, would open up, but since everything is with respect to x, we're going to open to the right versus the left. Okay, so I can see now the region bound by those two functions is this region right here. That's the area I'm looking for. So what I need to figure out then is, where do these two graphs intersect each other? Where am I going to integrate from and to? From what's the left side, the right side? What are the bounds? So I'm going to set these two equal to each other. 2y plus 4 equals y squared plus 1. I can see this as a quadratic, so I'll set it equal to 0. Y squared minus 2y minus 3 equals 0. If I factor this, I get y minus 3 and y plus 1. So I can see that the y values where they intersect are -1 and +3. Kind of makes sense. I can see it on my graph, -1 and +3. So I messed up a little bit on the top here, but that's supposed to be at +3. I'm going to integrate this along the y-axis, because this whole entire, all of these equations are all with respect to y. So it's x equals something in terms of y. So when I write my integral, I'm also going to write my integral so the bounds are also with respect to y. So if you think about the y-axis now, this would be the top function compared to this axis. And this would be the bottom function compared to this axis. So if you turn your paper as though this were now the new x-axis, this function's on the top and the curved one's on the bottom. So it's kind of interesting. I mean, it's not different than what we've been doing. You're just looking at it from a different perspective. You're looking at it horizontally instead of vertically. So the area between those two curves would be from -1 to 3. The top function is 2y plus 4 minus the bottom function, which is y squared plus 1. If we simplify this, I end up with -y squared plus 2y plus 3. And I'm going to integrate that. I'll actually do this one because you'll see it's no different. I'm going to still find the antiderivative, -1/3 y cubed plus y squared plus 3y. I will plug in -1 and I will plug in 3. So 3 cubed is 27 times -1/3 is -9 plus y squared, which is +9, plus 3 times 3, which is also 9. Now if I plug in -1, -1 cubed is -1 times -1/3. -1 squared is 1. 3 times -1, that's 9. This is -2. 9 minus -2 is 11 minus 1/3. You can leave it like that, or you can write it as 10 2/3. It doesn't matter. Both of those are correct. So that's the area between those two graphs. You're just looking at it from a different perspective, but it's all the same process. Okay, here we